In this section, we'll be talking about inverses of functions. To talk about inverses, we first need to discuss the idea of a one-to-one function. For one-to-one, every y coordinate is unique to every x coordinate. Whenever we would look at a set of points in the earlier parts of the chapter, we said that an x coordinate could not be duplicated, but a y coordinate could. Well, it sometimes is desirable for the y coordinate not to repeat. When we do this, that's whenever we have the property called one-to-one. Every input always has a unique output going to it. However, to go further, every output was unique to the input. That's the idea of a one-to-one function. You can say exactly one input to exactly one output, and no going backwards or forwards having more than one. One-to-one functions are also called invertible for reasons that will make sense momentarily. The horizontal line test. The horizontal line test says that a function is invertible if you could draw any horizontal line and none of them pass through the function more than once. Every one of them is going to go through it just one time. Let's just do a quick example. 3x plus 7 is a line, probably looks something like this. And if I were to draw horizontal lines, every one of them would only pass through one point. So this function is one-to-one. Whereas the graph of x squared, we know that's a parabola. And it's pretty clear that the parabola fails the one-to-one, the horizontal line test. So this is not one-to-one. And the final one is x cubed minus 2. Now if you remember transformations from 2 sections ago, this is the graph of x cubed and it's shifted down 2. So the graph is going to look something like this. And as you can see, this function is invertible. Every horizontal line passes through it only once. So this one is one-to-one. If a function's one-to-one or invertible, what we create is what we call the inverse. The inverse of the function is the one that undoes what the original function did. So it reverses the steps and undoes every step. And I can give you a little chart to make that easy and kind of see where they come from. Some of these can be done in your head. However, whenever we're doing this, we will sometimes need a harder technique. And it's not a hard technique, it's just that we might not be able to do it in our heads. One of the things that distinguishes the function is that if you form the composition between the function and the inverse, you get x in either order. And I should point out this notation. It looks like f raised to the negative 1 of x. This is really just f inverse is how we read it, and it has nothing to do with exponents. So just to point it out, x to the negative 1 does mean 1 over x. But f with a negative 1 is read f inverse, and it is the inverse of the function. Nothing to do with exponents, nothing to do with reciprocals. That means inverse. Let's figure out how to invert this function f of x equals 2x minus 3. The easiest way to do that is think about what the steps do. What's the first thing you do whenever you plug in a value? You multiply by 2. We do times 2 is our first step. And then our next step is we subtract 3. And then we end up with our output, f of x. So if we were going to reverse that, and we started with f of x, and we wanted to work our way backwards, well, to reverse the minus 3, we would add 3. To reverse the times 2, we would do divided by 2. And that would get us back to x. F of x would be, well, whatever we start with is x plus 3 divided by 2. There's your function. And so if I was to give that a name, we call that f inverse of x. Alright, so let's talk about how to do this in general. Remember that the idea is the input and output roles get switched. So why don't we switch the roles of x and y? That's how we can make this work. The way that we find an inverse is replace f of x with y, switch x and y, and then solve for y again. If we solve for y in that equation, we have the inverse. One point about this is when we switch x and y, we will now change the function so that it flips across the line y equals x. And I'll show you a picture of that in a moment. The official algorithm is first, change f of x to y. Then switch the roles of x and y. X equals negative 3y plus 4. Now just solve for y. Subtract 4 from both sides, and I get x minus 4 equals negative 3y. Divide by negative 3, and I get f inverse of x is equal to x minus 4 over negative 3, which if you were paying attention to the method that I did a moment ago, you can kind of see that answer. First we multiply by negative 3, then add 4. So really we subtract by 4 and then divide by negative 3. And that's what we end up with. X minus 3 cubed minus 1. So we have y equals x minus 3 cubed minus 1. And now we switch the roles of x and y. So x equals y minus 3 cubed minus 1. And now we need to solve for y, which is a little bit harder this time. Let's add 1 to both sides. And I get x plus 1 equals y minus 3 cubed. So what we really have to do is somehow get rid of the cube power. If you think about it, the thing that reverses a cube is a cube root. So what I end up with next is a cube root of x plus 1 equals y minus 3. And then adding 3 to both sides and not combining something that doesn't combine. Keep in mind, x plus 1 is inside of the cube root, the plus 3 is not, so this does not become x plus 4. This just becomes y equals the cube root of x plus 1 plus 3 on the outside of the cube root. That's my value for g inverse of x. That is going to be the cube root of x plus 1 plus 3. Next, h of x, the square root of x plus 2. This one is a little bit trickier than it looks, and I'll show you why. The square root of x plus 2, if we go through the steps, we get y equals the square root of x plus 2. We switch the roles of x and y. We square both sides to get rid of the square root. So far nothing has been too mysterious. Subtract 2 from both sides. And so my answer would be h inverse of x equals x squared minus 2. But there is a problem here that I did not say. Look at your final answer. X squared minus 2. What does that graph look like? X squared minus 2 is a parabola. Parabolas don't pass the horizontal line test. So somewhere, something went a little funny. It's actually right here. When we squared both sides, we potentially introduced an extraneous solution, just like when we squared both sides in the first chapter to solve a radical equation. How we remedy this is by paying attention to the y values and consequently restrict our domain. I notice here that y is greater than or equal to 0. If I restrict my y values in the original function and find a restriction on it, that will restrict my x values when I switch them. Take a look. When I switch x and y, now the y changes to an x and I have x is greater than or equal to 0, which carries through the whole time. And finally, even in my final answer, as long as x is greater than or equal to 0, this works. This will really only happen to you in the case of the square root. I don't plan to confuse you guys with these. They probably won't show up as a regular test question, but perhaps a bonus. When I have the square root and I square both sides, that's what leads me to this funny answer, and so I have to pay a little bit more attention to it. Here is the reverse of the idea that we just did a moment ago. There is a domain restriction because if that wasn't there, we wouldn't be able to take the inverse. Let's go through the steps. Y equals x plus 1 squared, x is greater than or equal to negative 1. Switch the roles of x and y. And now we've got y is greater than or equal to negative 1. We take the square root of both sides. We get the square root of x equals y plus 1, with y still greater than or equal to negative 1. And there's a very important thing here. Normally when you take the square root of a function, you need a plus or minus. That plus or minus, I'll go ahead and write in this case, but we need to pick one. Plus or minus is not going to give me a real defined function. However, since y is greater than or equal to negative 1, that means we can actually keep only the positive. So that's what those two do to each other. If the y values are greater than or equal to negative 1, the square root better be positive. Anyway, subtracting 1 from both sides, we get square root of x minus 1, and that's what I'll call the function j inverse of x. This last one, I'll set it up. If you didn't know what you were doing here and you had never seen this example, you would probably have a fair amount of difficulty solving this problem. But now that I've done the first two steps, let me show you the trick. I let k of x equal y, I switched x and y. You might be able to come up with the first step. I'm going to multiply both sides by 3y plus 4. And so when I do this, the 3y's plus 4 cancel out. And I can even distribute. I get 3xy plus 4x equals y minus 7. How in the world do you get y by itself here? The answer is we're going to do a very specific factoring method. And so what I'm going to do is I'm going to subtract y from both sides, which doesn't combine with anything. And I get 3xy minus y plus 4x equals negative 7. Subtract 4x from both sides. And in doing so, I get y's on one side and terms that don't have y's on the other side. So here's the magic. If I factor out the y, I can get it by itself. If I divide by 3x minus 1, I have an answer. Get the y's on one side, get the non-y's on the other side, factor out the y, and divide. And that will solve this problem. So to give a final answer, k inverse of x equals negative 4x minus 7 over 3x minus 1. These are for you to try, so feel free to pause this video and take a look, and I'll come back to help you with it in a moment. Okay, hopefully you had good luck on this. Let's go ahead and switch the function to y, and then switch the roles of x and y. Alright, so now let's get y by itself. We'll subtract 6 from both sides, and we get x minus 6 equals the cube root of y minus 2. Now this time we're going to cube both sides, but when you talk about odd roots, you don't have to do anything strange at all. You just cube both sides, and it works out exactly the way you would hope. So x minus 6 cubed equals y minus 2, and consequently the function L inverse of x is equal to x minus 6 cubed plus 2 when we add 2 to both sides. Alright, if you haven't done the next question, you should pause your video again and give it a try. And we get y equals 2x minus 3 over x minus 4. Switch the roles of the two variables. And multiply both sides by y minus 4, just like the last time we did this. We get xy minus 4x equals 2y minus 3. And so we'll subtract 2y from both sides, and since I've shown you this trick once before, let's go ahead and add 4x to both sides. That gives me xy minus 2y equals 4x minus 3. Factor out the y, and I'm left with x minus 2. And then divide by x minus 2. And I am given now y was m of x, so m inverse of x is 4x minus 3 over x minus 2. This last problem is also for you to try. You should be careful that the final answer is going to have a restriction on x, just like the last time we ran into a problem like this. Now that you've tried the problem, let's start out by remembering we're going to need to put a restriction on x. So to do that, I need to find the restriction on y. And in this case, y is going to be greater than or equal to 2 because the square root will be greater than or equal to 0. So we get y equals square root of x minus 1 plus 2. X equals the square root of y minus 1 plus 2. Subtract 2 from both sides to get x minus 2 equals the square root of y minus 1. Then we'll square both sides. And we get x minus 2 squared equals y minus 1. Now remember, the last time we did this introduced an extraneous solution. So let's copy these y bounds. When I switched my x and my y, that became x greater than or equal to 2. And that carries all the way through, just like before. And when I add 1 to both sides, I get n inverse of x equals x minus 2 squared plus 1 from adding 1 to both sides. And that's for x greater than or equal to 2. So one thing that might be enlightening here is let me draw you guys a picture. The square root function has been moved to the right 1 and up 2. According to our rules of transformations, it's going to look something like this for the original function. And the new function is x minus 2 squared plus 1, which is right 2 and up 1. But x is greater than or equal to 2, so it looks something like this. And here's where it all boils down. If I were to draw the diagonal line here, you'll notice that these are a reflection of each other in the diagonal line. The blue curve, its reflection is a quadratic, but only half of it. If we did not have the x greater than or equal to 2, we would end up including the whole rest of the quadratic function, which as you can see is not part of this reflection.